This is a somewhat tricky problem because this is really algebraic manipulation. We don't really have any values here. We're given the situation, and we want to find different values for different variables based on the variables that are given to us in the situation without knowing anything else. So for number one, the time elapsed from the instant the block leaves the table to the instant it strikes the floor. Again, we want to know the time, essentially how long it's in the air, from when it leaves the table to when it strikes the floor. So that's essentially a projectile motion problem, so we got to think of that. Well, what does the time in air depend on? It only depends on the vertical component. It doesn't matter how fast or necessarily how far it goes, how fast it leaves the table. It just depends on the height and, of course, the fact that there's gravity acting on it. It's accelerating at a rate of g. So our delta x, our displacement, is h. V naught, again, is 0 because it leaves the table horizontally, so the vertical component of the velocity is 0. Acceleration g, solve for t. So we plug it in using our kinematics equation, do, again, a little bit of algebraic manipulation, and we get t is equal to square root of 2h over g. Now I want to point out that 2h over g altogether, that whole fraction is inside the radical. Now for number two, find the horizontal component of the velocity. And again, now it starts to get a little bit tricky because we, depending on what we know, we kind of have to think logically about what makes sense here. So keep in mind we know the time, or at least the expression for time. And we actually do, in fact, know how far the mass lands from the edge of the table. It lands a distance d away from the edge of the table. So again, this is a kinematic situation here. We know that horizontally speaking, the velocity or speed is always constant. So speed equals distance over time. So d over, plug in our time value from number one. And in this case, at this point, it's just a little bit of math. And it turns out, since you're dividing by a radical, but more specifically a fraction, you can multiply by the reciprocal. So you can multiply the numerator and denominator by square root of g over 2h. And that completely gets rid of it from the denominator. So we're left with speed is equal to distance times square root of g over 2 times the height. For number three here, the work done on the block by the spring. Two equations for work, or two concepts really for work. Work is a change in energy, in this case kinetic energy, because the spring moves horizontally and causes the velocity to change and so forth, or force times distance. Now, unfortunately, we don't know force, and that's not, that's not one of the variables in the problem, so we're not going to look at that. So we're going to look at a change in kinetic energy. So right when the block leaves the table, it's got a speed, it's got a kinetic energy, so we're going to use 1/2 mv squared minus the initial kinetic energy. Well, it started from rest, so of course minus 0. So all I do is simply take the speed from number two, again, speed and velocity, essentially the same thing, just one's a scalar, one's a vector quantity, and plug it into our v value, and we do a little bit of math. Distribute the squared to the d component, and then the square root of g over 2h gets rid of the radical. So all in all, we end up with something along the lines of md squared g over 4h. Now your answer might look slightly different than that depending on how you simplified it, but either way will work as long as you did it correctly. Either answer will be accepted. To find the spring constant, again, we got to look at the fact that energy is really always conserved, except, of course, for collisions, which there is none here. But we know that initially there's potential in the spring. That gets converted to kinetic as the mass leaves the table. It's now moving, so all of that energy goes into kinetic in the block. So we have 1/2 kx squared equals 1/2 mv squared. We know x from the problem above. X is the compression of the spring, so that's the distance it goes, how it normally looks, and we plug in our value for the velocity, the kinetic energy right away. 1/2 mv squared. We already know the value for it, md squared g over 4h, and set that equal to 1/2 kx squared. A little bit of math, a little bit of work there shown, but you get something along the lines of md squared g over 2x squared h. Again, if your answer looks slightly different, but you set it up as is shown here, then it should be fine.